stuff you learn in school that I just don't listen to.
Like last year I did good.
I swear, it just feels like it got darker.
And massive reach.
Also cheesy.
Whoops, wrong one. Okay, so yesterday we started chapter 2, and we kind of got to the part where we talked about radioactivity and its useful applications, how you can take specific molecules, follow its fate. There's some downside to it, but you can also use isotopes to date extremely old things. So we talked a little bit about radioactive decay and half-lives. So then kind of going back to our little story of this idea of a life from chemical hypothesis, how old is Earth? Well, we have found some extremely old rocks, in Australia and Africa, and there is one here in Minnesota, just outside Granite Falls. And we've taken many samples, we've analyzed it, and so we kind of have a good idea of how old Earth is, about 4.5 billion years ago. So geologists use radioactive dating. If chemical evolution did take place, obviously it had to occur after Earth had formed, but before life began. Well, it's like, duh. So now you have to try to estimate when did that first life show up. So we have to look to the fossil records. And the oldest fossil that we have found is possibly this tiny little carbon molecules, from early photosynthetic organisms about 3.85 billion years ago, and that's based on radiometric dating. Heat and pressure eliminated of the original cells. The life just started after the end of this massive bombardment, which is like Earth formation. So there's this consensus that this chemical evolution happened in a very narrow window of 300 million years or less. And it's all from this evidence for radiometric dating. And like I said, it's a hypothesis. So we're still trying to gather information and search for other fossils.
I wouldn't say that's a very narrow window.
Well,
Like
in the time scale of Earth.
That's like 10% of the whole Earth's life.
Okay, so we've been talking about atoms, and we kind of discussed the nucleus with the protons and the neutrons, and so now we're going to talk a little bit about the electrons. And the main properties of electrons is to kind of determine what kind of, will the atom be reactive? Will it be unreactive? So we call this chemical behavior, and it's, again, determined by these electrons. So Bohr's model, back to Niels Bohr, kind of depicted electrons in these discrete circular orbits, kind of like planets orbiting a sun. So if this is my, nucleus, I have my electrons that are orbiting it, or maybe you might have seen diagrams like that as well. But the modern model does indicate that it's not possible to pinpoint exactly where an electron will be. And the reason for that is electrons travel extremely fast. Comes the speed of light there. So what we have instead for a model is an orbital model, which is kind of like an electron cloud. It gives you the probability of finding where an electron might be. Orbitals come in a variety of shapes, kind of like dumbbell shapes. So if this is my nucleus, instead of having, these arrays of electrons orbiting it, I might have shaded regions. So that might be a higher probability of finding the first 2 electrons in the energy level. And then now there's like these dumbbell shapes, and again, shaded. And wherever the areas overlap, the darkest regions, those are high probabilities of finding an electron. So these electrons are always moving. Again, you just can't pinpoint exactly where an electron might be, but you kind of have a probability of where you should find one. So regardless of shape, no orbital can have more than 2 electrons. So what I mean by is, I drew this sphere, only 2 electrons can be in there. I drew this dumbbell shape, only 2. And I mean, the shapes are crazy. I mean, then they go like this. Then there's like donut shapes, and there's more dumbbell shapes. It just gets super crazy. So atoms contain discrete energy levels, and this is why electrons don't crash into the nucleus, because electrons have a negative charge, protons have a positive charge, opposite charges attract. So they maintain a certain distance based on how much energy these electrons have. When electrons are found in the outer energy levels. That just means they have a higher, greater potential energy. So then when those outer electrons move closer to the nucleus, energy will be released. So I'm going to go back to my simple diagram. Oops, I used the wrong side. So my nucleus, these are energy levels. I'll draw one more. So here I have an electron out in the outermost energy level here. And if it moves closer to like the second energy level, we'll say, this process, going from outer to inner, releases energy. And then if there's an electron in the second energy level that gets moved to the third, well, now energy will be absorbed because you got to absorb energy and move it out there. Energy levels do correspond to quanta, which is a definition for just a specific amount of energy. So this diagram on the next slide kind of depicts this, energy levels, and when an electron is moved closer to the nucleus, energy is being released, and then when it is absorbed, it's moving out. So whenever you see like a light, say you're doing a chemical reaction and a light is given off. So like in chemistry, I'm sure you'll light magnesium strips or make things go boom, right? What's happening is electrons being transferred, released. So okay, gotta go back. All right, so this diagram right here is showing electron orbitals, and I drew a picture of the nucleus, and this is the first energy level, and these represent electrons, okay? So this first energy level is always considered an S, and S is like sphere shaped. So this is what this electron cloud looks like. It's just a sphere to represent the first energy level, okay? Now, this next slide right here, if I move to the second energy level, notice it has 8 electrons, okay? And here I have another sphere, so there's 2 electrons, because remember, each orbital can only hold 2, and now I have this dumbbell shaped, so there's 2 here, and then I have a dumbbell shape in a different orientation, there's 2 here, and then the dumbbell shape and down 2 here. So if I were to count the electrons just for this second energy level, 2, 4, 6, 8. So this is what that looks like. And then I still have the 1s, so you can kind of see the overlappage of the first energy level with the second. Okay, so this is what it looks like all together. And this is what it looks like when you combine all of these orbitals together. Crazy. So shaded region, high probability of finding an electron.
Big Bang Theory.
Yeah, absolutely. Do not confuse energy levels with orbitals. If you see rings, they're talking about energy levels or showing you where the electrons are energy level wise. Orbitals are the 3-dimensional shapes that tell you the probability of finding an electron. Okay, now I'm going to talk a little bit about the periodic table. You may have noticed, actually I'm going to go back to...
So the orbitals, is that like pinkish color, brown?
Yeah, the overlappage. I want to go back. Oh, no, where did I see it? It was on this. 1s. So you may have noticed this 1s. I think, did I put 2s for the next one? Yes. 2s, and then maybe you notice something called 2p. So in chemistry, when you get to the chapter about electrons, which I think is like chapter 3 in the chemistry book, but I don't know if Burke, it really doesn't use the chemistry book. The periodic table...
Amanda Lanter, come to the office, please. Amanda Lanter.
...is set up, again, to show orbitals. So not only do you have increasing number of protons, the columns represent the same number of outside electrons, which means kind of the similar properties, but you can also figure out the electron orbital or configurations of these atoms. So 1s is the first 2 columns because you can only hold 2 electrons in the first energy level. Okay, so S. Then we have the p blocks, which are the dumbbell shaped. And so 2p means second energy level dumbbells, okay? 3p would be third energy level dumbbell shaped. 4, 5, 6, 7. So as you go down, you're getting out to the outer regions of your electron energy levels. Then we have the D block. Those are our transition metals. And then we have the lanthanides and the actinides, which most of them are radioactive, but not all of them.
Doesn't the D block skip a level?
Yes, it does. Yep. Okay. So I created, like, I don't know, 40 some slides here. This is the reason why my lecture is 111 slides. It's mostly because of this part right here. And I put a lot of work into it, so. Okay. These represent energy levels, okay? And 1s means the first energy level that can just hold 2. And then these guys are 8. And then I even went to 3d to kind of show you what some of the first transition metals kind of look like. So we're going to use arrows pointed up and down to represent electrons. And you can only hold 2 electrons in each little square because those are orbitals. Notice my second energy level still has 8. 2, 4, 6, 8. And then 3s to 3p, 2, 4, 6, 8. And then this is where things get screwy because you'll probably learn that in chemistry, but I won't get that far, I don't think. Okay, so hydrogen has 1 proton, 1 electron. So when I draw this, it just has 1 electron in the s orbital. Helium, oops, sorry, forgot all about those arrows. Helium has 2 protons, 2 electrons. So then I go up, down. Is this energy level filled?
Yes.
Yeah, and this is why helium is stable. It doesn't react with anything. You know, if you're dealing with a very reactive substance, well, if you could surround it with helium gas, it won't react with helium gas, so it should remain more stable. So there's helium. Okay, now, helium really sits over here in the periodic table, but for simplicity's sake, I moved it over. All right, lithium, 3 protons, 3 electrons. So now I'm in the 2s. And there's that first electron. And lithium is located there. The 1s is filled. The next electron goes into the next sublevel, 2s. Again, note how Li, lithium, is 2s1. So this is not a full configuration yet. But now with beryllium, it is. Okay, so there's Be with 4.
So does that mean that beryllium is more stable than lithium?
It is. It's not as reactive as lithium. So lithium will give up that 1 electron. Beryllium has 2, but it will give those 2 up. It's just not as reactive as lithium. Lithium's like combustible.
I thought
With neon, that's going to be not like
Right, it's going to be completely filled.
in the second energy level, don't you have to have 8?
Right. Yes, you do. In the second energy level, you have to have 8. But I'm just saying that it's not as reactive as lithium because it was able to fill the sphere. I don't know what that said. You okay over there? Never mind. Okay. Moving on. Okay, so then now we're in boron, and there's 5. And there's carbon with 6. Okay, and here's nitrogen with 7. Here's oxygen. I really want to get to the first noble gas, which is neon. Okay, fluorine has 9. It just needs 1 more electron to be completely filled, and if it does, it acts like neon. Okay, why is it? Oh, I think it's frozen. There we go. Neon. All right, neon's a noble gas. It has 8 in the second energy level. It's inert, unreactive. Okay. So I could go on. There's sodium. Here's magnesium, aluminium, silicon, sulfur, chlorine, okay, argon, third noble gas we've covered so far. So, completely filled, inert. Okay, now I'm just gonna skip, so.
So all the noble gases always have full energy levels.
Yes, always.
So do they have different forms?
Do they have different
Like
forms?
carbon 12, like
Isotopes.
14, or isotopes.
Oh, you know what? I guess I've never looked. I think helium does have one.
Wait, what do you guys?
If they have different isotopes.
Okay.
That would
Maybe I should just like.
that would have
pause.
changed.
Okay, we're almost to the next noble gas. Ah, krypton.
Isotopes would change the number of neutrons.
Yes.
So that would change
Okay.
that.
No,
It would change your
electrons?
total
Oh,
mass, but it wouldn't
well,
change your
come
energy.
back.
Yeah,
Go
you're right.
back.
So what are we changing?
Okay.
What
An
changes?
ion.
So when atoms or elements gain or lose electrons, what's happening is a redox reaction. Okay. So during some chemical reaction, electrons will be transferred from one atom to another, and as a result, the one atom that gives it up obviously is going to lose that electron, and we call that oxidation. And then the element that gains the electron is called a reduction. So you have to know the difference between oxidation and reduction, and I do have a little mnemonic device you can use. It's called oil rig. Okay? Oxidation in loss, reduction in gain. Okay, so yeah, so here's this diagram that's showing the oxidation process. Here's element A, and it's going to give up that electron. So it's losing its electrons, it's become oxidized, and then element B gains that electron, thus being reduced. So this is another diagram that shows this oxidation reduction. So, yes, reducing agent gives up the electrons, becomes oxidized. This one gains, becomes reduced. All right, moving on to section 2.2. Woo.
Wait, reduction gains an electron?
Oil rig.
Yeah, wouldn't that make it bigger than though?
Okay, careful. It says reducing agent. Oh, wait, I see what you're saying. Gains electrons. Okay, B is gaining. Okay, so reducing agent means it's going to donate the electrons.
Okay.
Okay, and it becomes oxidized, so they lose oil. And then down here, they like flip it, so it's the okay. Maybe you should just forget this slide. Just forget this slide, okay? Because what they're doing is, okay, B gains the electron, so it's being reduced, but it's the oxidizing agent because it's causing it to lose its electrons. It's the reason why A lost the electrons.
Oh, okay.
Yeah, just forget it. Just remember oil rig.
Okay, I was
Okay. Okay, moving on. Elements found in living systems. So the periodic table was arranged by, well, a guy named Dmitry Mendeleev. And people were out to kind of create a chart with all known elements. And so Dmitry, what he actually did is he just had these little note cards, and he had elements, their names, their number of protons, just a bunch of information about them, and he started to rearrange them in a way that made sense. So he started to increase by number of protons, but then he also looked at a little bit of behavior, and he noticed that after every 8 elements, and he like went back, you could see like a pattern. So we call this the law of octaves. And if you look at the periodic table, 1, 2, skip this, 3, 4, 5, 6, 7, 8, repeat. So that's the law of octaves. So all group 1, super highly reactive. Group 2 is reactive, just not as dramatic as group 1. Skip the transition metals. Boron, aluminium, gallium, indium, they all react the same way. These guys can form 4 bonds. Nitrogen can form 3 bonds. Oxygen forms 2 bonds, this column. And these guys form 1 bond. Highly reactive. These are the most reactive non-metals. And then all of these guys are inert or unreactive.
So the negative ones are more reactive than the plus ones?
Oh, I wouldn't say more reactive. These guys are the most reactive metals.
Oh.
These guys are the most reactive non-metals.
Makes sense.
Okay. Periodic table also displays elements according to their atomic number. So it increases by atomic number, which tells you the number of protons, as well as its properties. So I've already mentioned this, but the columns represent properties, like they all behave the same way. And it's because of these valence electrons, or the outermost electrons found in their energy level. So we've discussed that the whole objective is to get 8 electrons, and the number of electrons determines the chemical behavior of that element to achieve 8. So if you have a filled energy level, that means 8 electrons, you are inert or non-reactive, which means you act like a noble gas. So magnesium and oxygen, well, magnesium has a +2, right? And oxygen has a -2. And if I wanted to draw this out, magnesium, see atomic number 12. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And then here's oxygen. Oxygen is 8. 1, 2, 3, 4, 5, 6. Whoops, did I say 8? Yep.
Yeah.
7, 8. So you notice that oxygen has an open space here and here. And magnesium wants to get rid of these two. So they transfer these electrons to the oxygen. And as a result, a chemical reaction takes place. And you can see light being given off. So we have a redox reaction taking place here. If you take magnesium and mix it with neon, which is a noble gas that has already a filled energy level, it's not going to do anything. It's just it's boring. Yeah. You guys ever taken magnesium ribbon and light it up? I'm sure you will with Rourke. It's kind of cool. Just don't look at it directly. You will see spots.
Kind of like when I stare at the sun.
Yeah, it's actually, I think it's brighter than that. It is. Whew. So I know you've seen this already. These diagrams just show the number of valence electrons. So lithium, which is in column 1, has 1 valence electron. Beryllium, which is found in column 2, has 2 valence electrons. Skip the transition metals. Boron, that column has 3. Carbon, they have 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And then you get your noble gas with a filled energy level, inert. So you may see Lewis dot diagrams. In fact, actually you won't. I don't think you'll see Lewis. You might see a test question. But you won't have to draw any. But if you saw this, I hope you would realize the dots represent valence electrons. So if I were to show you a picture and say, how many valence electrons are in the picture below? You'd say 2.
So valence electrons are just the ones that are laying on a full ring like that.
Right. They are in the outermost energy level, valence electrons. So like beryllium has 4, but we're only looking at the valence electrons, so there's 2.
Gotcha.
Okay. So the octet rule, trying to achieve 8 in order to fill their outer energy level. They want to be complete. This is why you can predict how they will behave. So sodium and chlorine is actually a very violent reaction to make salt. Sodium has 1 valence electron. It's found in group 1. And chlorine has 7 valence electrons found in group 17. And so sodium will give up that 1 valence electron to chlorine. Chlorine is filled. Sodium sheds that outer energy level. And so then it goes to the next level inside and it's filled. And they form a bond. Okay. Organic compounds are compounds that contain carbon, but they also consist usually of hydrogen, oxygen, and nitrogen, or CHOM. And so to give you an idea of how diverse organic compounds are, it primarily consists of the 4 macromolecules. You may have learned that in biology last year. Nucleic acids, lipids, carbs, proteins. And then you can break down each macromolecule even further with polypeptides, amino acids, insulin, enzymes. With carbs, it could be a monosaccharide, a disaccharide, or a polysaccharide. And then from there, things just get even crazier with all the names for sugar. Lipids are fats, usually 3 main groups: fats, phospholipids, steroids, and again, you can subcategorize them even further. And then nucleic acids with DNA, RNA, and all that.
let's do it, and then I got another layer.
Okay, nature of chemical bonds. So we're going to talk about how bonds are formed. Some terms you need to understand. So molecule and compounds. There is a difference between the two, because I can say a molecule of water, but then water is also considered a compound. So a molecule is just a group of atoms held together in a stable association. It could be hydrogen gas, nitrogen gas, water, or sugar. A compound means that the molecule contains atoms of more than one element, and it's got to be different. So hydrogen gas is not considered a compound because it doesn't consist of two or more different elements. It's the same. So this would be just a molecule. Water, well, it's a molecule because it's stable, but it's also considered a compound because you have hydrogen and oxygen atoms. Sugar has three different elements, carbon, hydrogen, oxygen, bonded together in a stable formation. So it's a compound and a molecule. So you could use those terms interactively with these two, but not with the first two. So there are different types of chemical bonds that hold atoms together, and the first one I want to talk about are ionic bonds. And ionic bonds, when they form, they tend to form crystals. So it's usually a non-metal bonded to a metal, or I should say metal bonded to a non-metal. So some examples, table salt, NaCl. I have a metal bonded to a non-metal. Calcium chloride. I have a metal bonded to a non-metal. I said calcium chloride for the wrong one. This is potassium chloride. Oh, yeah, I'm sorry. This is calcium chloride. This is potassium chloride. But again, metal bonded to a non-metal. In ionic bonds, they form opposite charges. So if sodium gives up that electron to chlorine, so let's just look at sodium here. Sodium is, the atomic number is 11, so that means I have 11 protons, and I have 11 electrons. How many valence electrons does sodium have? One, because it's in group 1. Okay, so I don't need to draw out the energy levels. You just look at the periodic table, say there's one valence electron. So I'm just going to put 1 VE down here. Chlorine, let's take a look at chlorine here. Atomic number 17. So I have 17 protons, 17 electrons. How many valence electrons does it have? 7, because it's 1 away from a noble gas.
Is that what that like orange or whatever color number is up there?
Yep.
Wait, what?
Right there.
Because it's in column 7, so there's 7. Oh.
So 7 valence electrons. So then when sodium gives up this valence electron for chlorine, now it will have 8, and we'll have a full outer energy cell. So really I can say 8, because now we're at a different energy level. But the number of electrons changed, right? So now I only have 10, because it gave that one up. And chlorine now has 18. And now what's the charge on sodium? If I have 11 protons to 10, it's a +1. What's the charge on chlorine? -1. So notice that the charges are the same number, but opposite. You can form an ionic bond. So the charges have to be the same. They have to balance each other out to form that bond. Calcium chloride is unique. If you look at the periodic table, what's the black number above calcium?
2.
A +2. And then chlorine, what's the black number above chlorine?
-1.
-1, but notice I have 2.
So it's actually minus.
So it's actually -2. And now the charges balance, and I have formed an ionic bond.
So if like there wasn't 2 and it was just the -1, they wouldn't bond.
Right, it would not be an ionic bond. In fact, I don't know what you'd have.
So it'd have to be a plus and then a minus.
Yep, it's got to be a plus and a minus, and they have the same total charge. Like, number
So it
wise.
just has to equal 0.
Right, it's got to equal 0. Very good.
It has to equal 0.
Yes.
Like
So one way
2
to
minus
tell whether or not you have an ionic bond is sometimes you can just look at the name.
2. No, because there's
They
2.
tend to end in IDE.
See that the other one there's +1, -1.
So we have an ionic compound that is electrically neutral because +2 - 2 equals 0. +1 - 1 equals 0. I was going to put -0. Wow, good goes. So then these atoms are arranged in a way that they attract each other. Plus are attracted to the negative. Because remember, same charges will repel. So then you get this crystallated structure. And that's why sugar, if you look underneath the microscope, are like perfect little cubes. So, yeah.
So table salt, is that also for the
Table salt is. Calcium is slightly different because of the 2 chlorines to 1 calcium. So then that's when you get like angles. But it's still a crystallated structure. So then to help you remember the difference, to help you remember ionic bonds, the name's bond, ionic bond. Taken, not shared. So there's no sharing of electrons here. They're being stolen. Okay, another type of bond, second type, covalent bonds. And these guys also can build stable molecules. Now, with ionic bonds, you can break that bond easily just by adding water. You add water to an ionic compound, the ions dissociate from each other. And then when you evaporate the water, they find each other and form crystal structure. So like sometimes if you leave wheat and water in a cup for a long period of time, right, and then all of a sudden you see this like grime, well, it's probably some magnesium ions and something else. Yeah, so, yeah. I don't know what Herman's water's like. But
Probably worse.
no comment.
No, their mic's off.
Yeah, because after we heard them talking the talk.
Oh, they shut their mic off, so they can actually hear us.
Oh yeah, they're just creeping right now.
Yeah, they're creeping. Bunch of stalkers over there.
Hi.
Okay.
Also they're unmuted.
Okay, covalent bonds, so they build stable molecules. What's happening in a covalent bond is that electrons are actually being shared, okay? So 2 atoms share 1 or more pairs of valence electrons. So I'm going to draw hydrogen because that's simple. Hydrogen, it's got the single electron, and here's another hydrogen, single electron, but the first energy level can hold 2, so it just needs 1 more. Same thing with this guy over here, and they're like, hey, let's share them. So then they actually end up sharing their electrons. So we call this a covalent. Nothing's being transferred or stolen. They are sharing these electrons. And sometimes they can share equally or unequally, so we'll talk about that. But they are stable for 3 main reasons. There's no net charge. The octet rule is satisfied, or in this case, first energy level can only hold 2. And it has no unpaired electrons. So, I guess I drew a diagram down here. There's my electron, and they decide to share. And so this electron will frequently orbit that at a nucleus. So.
Wait, so does this only happen with same elements?
This will not happen with, it doesn't happen with the first 2, I would say, because these guys are highly reactive metals. They will always give up those 2. It happens usually with those that are closer to 8. So carbon for sure, depends on group 13. Nitrogen for sure.
Like carbon and silicon.
So kind of this area right here.
They're both like carbon and silicon.
They both have 4 valence electrons, so they will form.
They could covalent bond.
Yeah, they could bond together. Yeah.
Well, could they also?
Wait,
they
have
could
the
also
same
ionic bond, couldn't they? If you transfer it, you make a full ring.
I suppose, yeah.
Wait.
That would be a lot of it. I don't know an example of that. CNA4?
Because
I don't know if I've ever seen
if
that.
carbon transferred, it would go 4 over the other side, and that one would already have 4 sides.
Mhm.
8. And then one would be down.
Hold on, I'm gonna make a note for tomorrow. I'm just gonna see if there's such a molecule, CNA4.
Wait, so Miss Erickson, they have to be in the same column to do the covalent bonds?
No, they do not.
Okay.
Okay, so here's an example. Let's look at carbon and nitrogen. Okay? So if I draw carbon out, I have 2 valence electrons in the first energy level, and then 4 in the second, because carbon has 6 electrons total. So 1, 2, 3, 4, 5, 6. And then nitrogen has 7, right? So 1, 2, 3, 4, 5, 6, 7. So nitrogen has 3 open spots. And carbon has 4 open spots. Okay? So then what happens is that these guys, they form a bond, so like they can form a triple bond. So this can be shared with this guy. This electron can be shared with this electron, and So it's going to look something like this. Okay, there, I think I got it. Yeah. So they actually form a triple bond.
Doesn't that carbon have another one left over though from the top?
Is that even legal?
Is that even legal? It is. So like the electrons kind of just get redistributed so that they can both be happy. So if I look at this outermost region, okay, 2, 4, 6, 8, and then nitrogen 2, 4, 6, 8.
So I feel like a covalent bond can that form with a lot of different elements.
It can.
Just because of the way you can kind of rig it.
Yeah.
So pretty much they just do whatever they want.
So here's an example of 2 chlorines being bonded together. Chlorine by itself is unstable because it just needs one more, but they can share. And so this denotes the shared electrons to become stable chlorine gas. Now the strength of covalent bonds does depend on the number of shared electrons. Single bonds are the weakest. Double bonds in the middle, triple bonds, really, really strong. So if you ever see, 2 dots in between 2 or a dash, that means a single bond. A double bond, you'll see 2 pairs of electrons between 2 atoms or 2 dashes. And then that triple bond is 3 pairs.
So there can never be a quadruple bond.
2 chlorines possibly bonded together, but it's highly unlikely. I mean, did I say chlorines? I didn't say carbons. Okay, there are molecules that have several covalent bonds. So one example is methane. So carbon has this unique ability to make 4 bonds. And so like methane CH4, well, you have a hydrogen on each one of those valence electrons to fulfill the octet for each element. C2H5OH. And also, there's lots of multiple bonds here. So here I have 2 carbons. It would look something like this.
Wait, why is there a double?
Well, here I'll draw in the valence electrons. 2, 4, 6, 2, 4, 6, 8, then 2, 4, 6, 8, and 2, 4, 6, 8. And these guys just need 2, 2, 2, 2, 2. But I don't think you'll need to draw any diagrams. But in chemistry, I'm sure Mr. Rourke will make you. I'm going to make my kids draw, so. Okay, there are 2 different types of covalent bonds, polar and nonpolar. And so remember, in a covalent bonds, electrons are being shared, but how equally are they being shared? So if I were to bring in a pan of brownies, and I'm like, oh, I'm going to share with you guys, and I just give you each a sliver, and I keep the rest to myself, I'm still sharing, just not equally. So we call that polar covalent, where one atom or one element kind of hogs the electrons. As you can see with the penguin and the polar bear, chlorine has a higher pull to that electron that hydrogen is sharing with it. In a non-polar covalent bonds, the atoms or elements involved are sharing those electrons equally. So then I would take my pan of brownies and cut it up equally, and everyone would get a piece. Okay? Same thing with this hydrogen gas, penguins. So how can you determine whether or not the bond formed will be polar or nonpolar? You have to look at something called the electronegativity, which means the affinity of the nuclei for valence electrons, this pull or attractiveness to valence electrons. So a nucleus that is more electronegative or has a higher electronegativity value has a greater pull on those electrons, and you can kind of, look at the values and guess, not guess, but figure out if it would be nonpolar or polar. So En stands for electronegativity, increases left to right across the periodic table and decreases down the columns of the table. Elements in the upper right-hand corner, so like fluorine and chlorine and oxygen and sulfur, tend to have the highest electronegativity values. So this next slide shows you electronegativity values of elements in the
So
periodic
they
table.
pull it more than.
They pull it more. So over here are my elements that have greater electronegativity values. So you can see that it increases as you go across and tends to decrease as you go down.
So the smallest one would be like in the bottom.
Yep. It's easy.
Hey, why is France not?
Good question. I don't know.
Because they're all radioactive. The ones in the bottom.
Could be. That's probably it. All right, nonpolar. So the affinity for electrons is the same. So you look at the values, and if you subtract the values from each other, and if it's within a certain range, and I think it's 0 to 0.5, then it would be nonpolar. And if it's
Can I have your
0.5
attention for
to
announcements,
2.1,
please?
it would be polar.
Seniors thinking of retaking the ACT in October. The registration deadline
Wait, can you
is
say that
approaching.
those numbers?
Students is younger
0 to
and desire
0.5
help registering
nonpolar.
or would like to prep book. Juniors, the P test will be
2.1.
administered in Wheaton in October. There is a $16 fee associated with this test directed towards students interested in pursuing a 4-year college degree or competing for a national merit scholarship. That way the counseling office for
Wait,
details.
so what if it's more than 2?
Jim from the Gazette will be
It's
here to
ionic.
take pictures of the homecoming candidates Thursday morning during break.
No longer covalent. Good
The
question.
jersey auction will be on Thursday, so bring your
Okay.
money so you can bid. Seniors applying for
Herman, you still with us?
college soon. You may be able to save the $20 application fee by holding on to your application
Okay.
for a few weeks.
We are actually going to end class right now because we have class meetings to prepare for homecoming. So I'll just stop the lecture and we'll just carry on. Looks like the lab will start Friday.
Seniors with younger men are for your advanced makeup list or do you
This is